Welcome to From Ones and Zeros to Trig. This is going to be a beginner level introduction to how computers calculate sine and cosine, mainly focusing on the ideas behind it with some Minecraft representations. Minecraft Redstone is a great way to get a better understanding of circuits and experiment with new or old ideas. So enjoy. Okay, let's start with how we're going to represent our numbers. The answer is binary. You've probably heard of a number, but these numbers are in base 10, meaning that we have the ones place, the tens place, the hundreds place, and so on. And so we count how many 10 to the x's can fit into our number and place those in its according places. But we don't have 10 inputs to represent the value of each place. Rather, we have 2, on or off. So we use a different number system, base 2 or binary. On will represent a 1 and off will represent a 0. Our places will be 2 to the 0, 2 to the 1, 2 to the 2, and so on. Let's do an example conversion from base 10 to 2. Take 41. Well, the highest power of 2 we can fit into it is 32, or 2 to the 5. 41 minus 32 is 9. We can fit an 8 into it, which is 2 to the 3, and then a 1, which is 2 to the 0. So then we have 1, 0, 1, 0, 0, 1. Okay, great. We have numbers, but to do trig, we're using a modified version of the cordic algorithm, which we'll go into later, so we need some more components. We need addition and subtraction. Let's start by adding two binary numbers, say 3 and 4. Remember, we have to keep track of the carry bits as we go, just like normal addition. But how can we make Minecraft do that? Let's pretend we have two inputs, A and B, and a third input, C, which is our carry bit. We're basically adding A and B together and then adding C on top of that. Here's how that works in logic terms. When we add A and B, the sum bit, the actual output, is 1 only when exactly one of them is on. That's an XOR gate. But when both A and B are on, we don't output 1 here. Instead, we create a carry which gets passed on to the next bit. That's an AND gate. So for 2 bits, our sum is A XOR B, and our carry is A and B. Then we also add the carry input C using the same idea. The final sum will be A XOR B XOR C. The final carry will be A and B or C and A XOR B. So the final carry keeps moving along. It propagates up the chain and turns off only when neither A nor B is on, because then there's nothing to carry anymore. At that point, something gets printed to the output. That's when the sum bit becomes 1. If we later find another spot where both A and B are on again, the carry turns back on and continues up. So in Minecraft, we're basically chaining together a bunch of these tiny adders, each one built with an XOR and an OR gate, to make a full binary adder that can handle any number that you throw at it. This is what it looks like in Minecraft. On the side here we have our carry tower, which is only cancelled in the event that both A and B are off. We take all of our inputs and compare them to get our output. Okay, that's one down, but we still need to figure out subtraction. Well, subtraction is just adding a negative number to a positive number, right? Well, here we can take advantage of something called the 2's complement rule. Let's look at an example. In Redstone, everything is basically done in mod 256, because that's the highest we can go, or because it's 2 to the 8, under the constraints of Redstone. For example, 7 mod 256 is just 7, 256 mod 256 is just 0, because that's where we overflow. All ones, or 255 mod 256 is all ones, or 255, which is our highest number. Now imagine we have a number 1001 plus A equals 0 mod 256. Let's figure out what this A should be. Well, we know that 9 plus A equals 0, which means that a should be negative 9. So is negative 9 just 1, 0, 0, 0, 1, 0, 0, 1? Because in binary we usually let the first bit represent the sign. Well, let's try that. 1001 plus 10001001 equals 10010010. I don't know about you, but that does not look like a 0. The reason for that is that computers don't know what to do with that negative sign bit in the front. In our human eyes that looks great, but for computers they think it's just another number to add. So you have to think of another way. Well, another way to represent a is with 256 minus 9. That should just give us 256 mod 256 equals 0 and work. And so it does. We find that this works for pretty much any number. Try 15 minus 8 equals 7 mod 256. Well, 15 plus 256 minus 8 also equals 7 mod 256. What does that 256 minus 8 look like in binary? Well, it looks like the inverse of 8 plus 1, and so that's 2's complement. You can turn an adder into a subtractor by reversing one of the inputs and adding 1 to it, aka what this is. Negative numbers are created by flipping inputs and adding 1. But you want to make sure that you convert it back to normal by adding 1 and reversing your output when the output is negative. Otherwise, it just looks like a really big positive number. Okay, so we've got all the parts, but how do we actually calculate anything? You might remember the unit circle from math class. The circle has a radius of 1. If you rotate a point around that circle, the x-coordinate gives you cos theta and the y-coordinate gives you sine theta. Now, what cordic does is basically simulate that rotation, but without using any multiplication or division. Instead, it uses only addition, subtraction, and bit shifts. We start at the point 1, 0, that's like an angle of 0 degrees. Then we slowly rotate that vector by small fixed amounts until we reach the target angle. After each small rotation, we check whether we've gone too far or not far enough, and then rotate in the opposite direction if needed. By the end, the x value represents cos theta and the y value represents sine theta. But first we have to convert the angle. In cordic, we don't work with degrees or radians directly. Instead, we convert the angle into a fixed point representation, usually an 8-bit value. Why? Well, because the algorithm works with discrete steps in binary math. For 8-bit numbers, 0 equals 0 degrees, 64 equals 90 degrees, 128 equals 180 degrees, 192 equals 270 degrees, and 255 is about 360 degrees, which is the point at which we wrap around. The formula is theta input equals the angle in degrees over 360 times 256, rounded to the nearest integer value. This scales the real-world angle into a number that cordic logic can use directly, keeping everything in binary and avoiding floating point math. But we first have to define a few variables we're going to use. X and y will be the coordinates of our current vector. Z is the remaining angle we need to still rotate. D is the direction we rotate this step. If z is greater than 0, we haven't rotated enough, so we rotate counterclockwise and d equals positive 1. If z is less than 0, we've rotated too far, so we rotate clockwise and d equals negative 1. Think of d as basically an indicator function. Mathematically, rotating a vector by some small angle alpha looks like this. X prime equals x times cos alpha minus y times sine alpha, and y prime equals y times cos alpha plus x times sine alpha. We can factor out the cos alpha term. X prime equals cos alpha times x minus y tan alpha, and y prime equals cos alpha times y plus x tan alpha. The outer cos alpha just scales everything slightly, so instead of applying it each step, we can handle it once at the end with a constant k. Because all the small angles alpha are fixed in advance, k depends only on how many iterations we have. After 4 to 6 rotations, k is about 0.607, so we can just pre-scale our x by that value. Here's the trick that removes multiplication and division. For small angles, tan alpha is approximated by 2 to the negative I. That means that we can replace multiplication and division with simple bit shifts, aka x prime equals x minus d onto y shifted by I, and y prime equals y plus d times x shifted by I. There's no multiplication, no division, just shifting bits. Now, how do we know what angle we rotated each step? We use pre-computed arctan values. Alpha I equals arctan 2 to the negative I. We store all these alpha I values in an array. For example, arctan 1, arctan 1 half, arctan 1 fourth, arctan 1 eighth, etc. On each step, we rotate by alpha I or negative alpha I, depending on the sign of d, and update the remaining angle, so z equals z minus d times alpha I. This tells us how far we still need to go. So to summarize, convert the input angle to a fixed point binary so the algorithm can work in 8-bit logic. Start at 1, 0. Use the pre-computed arctan 2 to the negative I values as your small rotation angles. On each step, decide d from the sign of z. Update x and y using add, subtract, and bit shifts. Update z using z equals z minus d times alpha I. After enough steps, x equals cos theta and y equals sine theta. There's no multiplication or division anywhere. This method lets you rotate a point on the unit circle entirely using simple binary logic, which is why cordic is perfect for low-power processors, FPGAs, or even logic gates in Minecraft. So in Minecraft, we have these sort of units. Each one has 3 inputs, x, y, and z. X and y both get shifted down the according number of bits depending on which iteration we're on. So for the first one, it's not shifted, but for the second one, it is shifted 1 down, and so on. We have these toggleable CCAs, so when this switch is turned on here, it basically turns into a subtractor by inversing the input and turning on the carry in. We control that switch depending on if the sign bit of the z is positive or negative, and then we get the output of 1 and then funnel it into the next. We also change the arctan value on the CCA that takes z as one of its inputs, depending on which iteration we're on. So let's try, for example, 120 degrees. Well, using the conversion from earlier, we divide by 360 and multiply by 256 to get 01010101 as our starting z value. Our starting x is just this, which is 0.607, and our starting y is 0. Let's jump to the end. We divide this number by 256 to appropriately descale it, so then we get sine of 120 is equal to 0.69 and cos of 120 is equal to 0.39. So that's not super accurate, but it's also not extremely far off. With a few more iterations and some more bits to hold more precise numbers, it could definitely be a lot more accurate, but conceptually this is basically how computers are able to calculate sine and cosine.